Right, so last bit, won't take very long. The equal areas rule. So let's just revisit a problem like this. So no more traffic. We've got this type of PDE, there's the initial condition. These are the characteristics equations, we solve them when we get to that. And for this initial condition, that's the implicit solution. If I look at it, I'd have to square that out, multiply up, I get a cubic for u. Right, so it's a cubic for u, let's just leave it like that. Right. So what's going to happen? Let's just think about this. So the characteristics equations are here. That says that u is constant along the characteristics. This means that we can integrate that to get x is x0 plus ut. Characteristics are straight lines. And if I look at my initial condition here, right, so this is f of x against x. It's x divided by that. When x gets big, this goes to 0. When x is small, it's basically x. So the initial condition looks something like that. All right, now what happens, of course, is that in this particular problem is given that dx dt is u, where u is positive, then I have effectively a speed associated with a characteristic. That's the speed at which information is being transferred. Right? That's going to be going that way if u is positive, so that's going to be going that way, and that's going to be going the fastest rate. Down here, we've got a negative value of u, so that's going to be going that way, and that's going to be going that way at the greatest speed. And then these things are going to be going at slightly smaller speeds. So qualitatively, I can predict what happens. I can just draw in a sample evolution. Here's my initial condition. This thing has to move that way. That one goes that way. And at some point, oops, I should have drawn it the same way on both sides. At some point, the thing's going to bend over on both sides. Right, so this is u against t. So we get shock steepening on both sides. So that's what's going to happen here. All right, now I can figure out when the shock forms. The divergence of the derivative. Here's the derivative, right? So I can differentiate all of that. Ux is equal to f primed of x naught. So I'd use the chain rule, rearrange, and just as we did at some point previously, we end up with this equation for the derivative. So I look for the largest, that's a plus, the largest negative value of f primed of x naught, and that gives me t is ts, the shock formation time. That's the algorithm. Now, even though we've got this kind of complicated solution here because we don't want to solve a cubic, we can perform this calculation. So let's just do that. So there's f primed. Well, if I just quickly do that, it's going to be product and differentiate there, or I can differentiate there. Which gives me this. So this is, if I write it as a single fraction, it's 1 minus x squared over 1 plus x squared. And so the exercise is figuring out where that's greatest. So that means I have to do it again. And I have to differentiate again, find out where the maximum of this is. So doing the same thing again. And that's the derivative of that. And then I can put that to 0 and figure out where the extrema are, and then I can calculate the value of that. Okay, so at this point, I know that I can calculate something out of that. I know I ought to be able to find out what TS is. Right, so that's when, as this thing's tilting over, it first becomes vertical on that side, and I should get both values out. Okay. I'm not interested in that. What I'm actually interested in is the equal areas rule. So let's continue more qualitatively. So I'm not going to go through any more detailed calculation. The calculation of the shock formation point is sort of the last analytical thing that I can do here, because I've got this implicit solution. There's not much else I can do beyond that. However, I can proceed qualitatively. Now, one thing I can predict from the current argument is that we get a shock forming. In fact, we get two shocks forming. Now, it ought to be clear from the construction that the values of U on either side of the shock are not the same, and they change in time. All right, so let's just recall what the shock speed was. So if I have a jump from U minus to U plus, then I throw in U plus and U minus into the flux here and put it into the denominator. That's what the speed is. And for this particular problem, J is 1/2 U squared. So if I take that and throw that into there, I can actually compute that this is 1/2 of U plus U minus. Right, that's putting that in there and factorizing, cancelling off a U plus minus U minus. So that's what the shock speed is. Okay, and so, right, I've got these values on either side, but if I just sort of sketch the multi-valued solution that I'm obviously going to get, right, it's going to be bent round here, it's going to go through there, bent round there, something like that. What I have to do is I've got to somehow come along and put a shock in here so that I get a single-valued solution. So I come up here, I hit that, I jump down, and I go there. Similarly, I'm going to put one in here. So this is going to cure the multivaluedness at the expense of having two shocks. But where do I put the shocks is the question. And in fact, as these things move around, you can imagine that they're going to travel around on this curve a little bit. And so these things are going to be functions of time. And we don't have an explicit expression for them. So I can't really proceed analytically in any way. So what do I do? This is where the equal areas rule comes in, which is a geometrical construction. So let's just derive what it is. Okay. Let's keep this picture. Okay, so we have a conservation law, and the more fundamental version of it, as I explained before, is not the differential version of it, it's actually the integral version of it. So let's just think about the integral version of it for a moment. And we'll make one simplification, which is that we'll just throw away any sources in 6. So coming back over here, the integral conservation law, that's d by dt of the integral from a to b of rho dx is equal to j between A and B with a minus sign. S is equal to 0 here. So that's what we're going to have a quick look at. Now, what I'm actually going to do is I'm now going to say that A and B are going to correspond to taking the whole interval, the whole line. So A goes to minus infinity, B goes to plus infinity. That says that d by dt of this equals, now I've got flux at minus infinity, flux at plus infinity. If there's no net flux into or out of the interval, then that would mean that j at minus infinity and j at plus infinity are either 0 or exactly match. So there's no net outflux or influx. Right, so we'll deal with that situation. Okay. Now, for our particular problem, right, we've got that rho is equivalent to u. And j was 1/2 u squared, but u was going to 0, so j went to 0 for x going to plus or minus infinity. All right, so that's all consistent with this. Right, but what does it mean? Well, it means that if this is 0, then the integral of rho dx, the integral of rho dx is fixed in time. So the total stuff is fixed and given by the initial condition. So in other words, the integral from minus infinity of rho dx is the integral of rho of x at 0, which is what I was calling f of x, dx. That's for all time. That means the area under the curve rho of x and t, so x varying, t fixed, all right, the snapshot, all right. The area under this curve is fixed. Right, so if I freeze time, look in x, the area under that curve has got to be the same. All right, so no matter where I put these shocks, I must do it in order that the net signed area, the area under the curve, has to be the same as what it was to begin with. And what it was to begin with, well, that was, of course, just this. So I'll draw it down here, right? There was this thing. Right, so that was t is 0. All right, so there's a net area under the curve there. And in fact, for x over 1 plus x squared, that's an odd function. The integral of f of x dx has to be 0. Right, so whatever I get from looking at the signed area of this thing, the multi-valued thing, when I chop it and insert shocks to make it single-valued, I have to get no signed area underneath it. So how can I do that? Well, it's actually quite straightforward. I'm going to perform an equal areas construction based upon the multi-valued bit of the curve. So let's just consider this part to begin with. We can enforce the constraint by an equal areas construction. So here we go. We've got this thing coming through, bending over like something like that, right? What's the equal areas construction? Well, I'm just going to put a vertical line in here so that this area equals that area. This guarantees that the area is conserved on that side. And then I can just do it on the other side as well. If I come down here, there's this one here, so I just put it in there as well. I match up the area there with there. Qualitatively, that says that that's where the shock must be. So I know how to easily calculate the multi-valued solution here because that followed from looking at the implicit solution. I may not be able to explicitly write it down in analytical form, but it's effortless to draw it. So I draw the curve. Here it is. It's got this loopy bit in it there and there. I just simply shove in a vertical line, match up the areas on each side. That's where the shock has to be. So that's going to be X star, and that's going to be X star there. Let's put minus there and plus there to indicate there's two of them, one on either side. So this gives the shock position, or positions here. And it's qualitatively more than anything. Right, so if you think about it, this guarantees, since everything's symmetrical, right, that I get constant area in time, and in particular, it's equal to the initial condition. Okay, so at that particular point, we could go into a little bit more detail about a specific example, which I'll give a few more details in the notes. However, I'm done.